Yes. Okay. Well, thanks. Thanks for your introduction and good morning again. This project is a collaboration between fellow students Eslam Elnikety and Aastha Mehta, my two advisors Deepak, Garg, and Peter Druschel, and our collaborators Rodrigo, Rodrigues, Johannes, Gehrke, and Ansley post. And Guardat is about enforcing confidentiality, integrity, and access accounting policies at the storage layer, protecting a system's persistent state and data. So shown here are recent news headlines about attacks and data leaks affecting web services. Such events are usually costly and embarrassing for the web server providers. Some of them have led to data loss. While there are many reasons for such incidents, in the following slides, I will explain common examples, and throughout the talk, we will see how Guardat can help to protect against them. The first threat is about unauthorized access. And unauthorized access occurs when clients are able to access content they are not allowed to see. This could be due to a configuration error, for example, an application access control list, or a bug in the application access check, a malicious attacker who circumvents the access control letter. In the second threat, I focus on state corruption. Here, the persistent state, consisting of content and configuration files, gets corrupted, violating their data integrity. Again, this could be due to a configuration error, a bug in the application or file system, or a malicious attacker that updates the content. A closely related threat is about code and log integrity. Here, an attacker would try to replace an executable with a Trojan such that he can persist across reboots. To avoid getting caught, the attacker also may manipulate the log to cover his tracks. As a result, it is hard to recover from such an attack without complete reinstall of the system. Website operators themselves have legitimate reasons to occasionally access client content, for example, for troubleshooting. This, however, gives employees the privilege to access and spy on particular clients. For these reasons, website providers usually have privacy policies that require logging and later auditing when accessing client content. However, this is very difficult to enforce in today's systems because employees usually have multiple ways to access client data. So let me summarize quickly. I have shown example threats in web services, but they exist more broadly as well. So let us try to understand for 1 second why these threats are hard to mitigate. As seen, the confidentiality and integrity depend on a large and fast-evolving code base, especially in web scenarios. Furthermore, access control lists and access checks spread across the entire software stack. Access checks, for example, could be implicit in application code or in the file system. And once state is actually corrupted, it is very difficult to recover from it. It requires you to maintain frequent offline backups, and even if you recover, the data may be stale or it is irreversibly lost. With Guardat, we focus on protecting the persistent state of a system such that unauthorized accesses don't occur and state is never corrupted. Guardat ensures the confidentiality and integrity at the storage layer for all the persistent stored data. This is, for example, files. Guardat builds upon a trusted controller in the storage layer to intercept all reads and writes to these files. The stakeholders of the system, users, providers, developers, and privacy officers, associate policies for every file. A policy states the conditions when a file can be read or modified. Guardat can attest the protection that is in place back to the stakeholders through cryptographically signed certificates. Using this attestation, stakeholders don't have to rely on any intermediate layers, allowing application, the operating system, and file system to be untrusted. When we are using Guardat, we are able to protect against the threats I just showed. And more generally, Guardat can protect the persistent state of a system from unauthorized access and state corruption. In this talk, I will focus on the web servers examples, though. So throughout this talk, I will explain the 4 key ideas behind Guardat. As first, I will describe the declarative policy language and show example policies that address the threats I just mentioned. Afterwards, I will focus on the enforcement of these policies and explain file attestation. Finally, I will introduce our concept Guardat Transactions that transform a file from one policy compliant state into the next atomically. So let's start with a declarative policy language. The goals are to define policies at a high layer such that confidentiality and integrity can be specified in a concise manner and are easy to audit. Moreover, the policy enforcement needs to be efficient due to its frequent invocations. We choose to base our language on data log, which is a common foundation for policy languages. A policy in Guardat consists of 4 permissions. Each is a Boolean expression over predicates. The read permission states the confidentiality guarantee, the update permission states the integrity guarantee. Set policy permission governs when a policy can be changed, and destroy governs when a file name can be reused. In the interest of time, I will introduce the predicates throughout the examples that address the threats that I mentioned earlier. One of the threats was about unauthorized access to private content files. Our policies here allows to read policy allow a read policy change or reuse of the file name only as part of a secure session that authenticates as Alice. With Guardat in place, the policy ensures that only Alice is allowed to read the file as long as Alice's key is not compromised. Here, as you can see, we only need a single predicate, session is, to create access control-based policies. The next policy protects the integrity of the file. In our example here, only Alice is allowed to update the file again through a secure session. These 2 examples I just showed provide confidentiality and integrity policies based on access control. So before I go over the next few policies, let me remind you that they will become more complex and not as hard to follow if you try to read them. So I'd like to refer you to the paper or ask me later for details. In another threat, the attacker tried to install Trojans within existing executables, violating their code integrity. In Guardat, executables can be protected such that only signed vendor updates are allowed. An attacker would fail to update the executable since it is impossible to forge the certificate without the vendor's signing key. The predicates used in this example access information about the file, content hashes, and the third-party certificate. The next policy allows appends only. When an attacker tries to modify existing log entries, he would fail because it's not an append-only update. We add an exception here for administrators to be able to truncate the log. Yes. So this policy goes beyond simple access control and instead actually enforces a structural integrity invariant. For this particular policy, we added features such that you can access the list of updates and compare them to the existing file. In our last thread, we have seen that providers have legitimate reasons to access clients' private data, but they require proper access accounting. Guardat can enforce mandatory access logging on content files. So first of all, we protect the access log to be append-only. And secondly, access to the content file itself is only allowed once a corresponding log entry has been written into the log file. Similarly to append-only log files, here we also had an exemption for truncation such that audit parties, after they finish their auditing process, are allowed to truncate the log. Okay. So these 5 examples have shown how to overcome the threats that I mentioned during the introduction. But I only talked about policies and not about the enforcement. So let's see where we could enforce these policies. There is a potential to enforce policies in the entire software stack. For example, in the application, as a library, in the operating file system, at an hypervisor through a virtual device, or in the storage layer. We chose the storage layer for 2 key points. First, the lower the enforcement is in the system, the less risk of circumvention. This becomes apparent once you think about implementing the enforcement in an application library. It can easily be circumvented by accessing the persistent data directly at the file system. And secondly, the storage layer enforcement allows a scalable system configuration where all policy-compliant components are placed in a physically protected machine room. Thus, only personnel with access to that room would be needed to be trusted. The client machines, enterprise network, and the personnel without access to the room wouldn't be trusted. This gives us a very strong threat model. Enforcing at the storage layer really means enforcing at the block layer. Let's recall that policies are associated with files. So now we have a mismatch between the enforcement and the policy association. File attestation helps to bridge this gap. In Guardat itself, we maintain a mapping between blocks and their associated policies in non-volatile memory, currently in Flash. Using this metadata, the trusted controller enforces the policies in effect for every access. But how do the stakeholders actually know whether their policy is in effect for a particular file? Well, Guardat attests the policy in effect for a particular file, generating a cryptographically signed certificate, showing the file name, the associated policy, the state, and a content hash or content. Stakeholders can then do an end-to-end check such that what they have written actually reached Guardat and the correct policy is enforced. With this in place, stakeholders don't have to rely on the intermediate layers and thus don't trust the application, file system, or operating system. So far, we have overlooked that demonstrating policy compliance often requires multiple read and write accesses. For this, we introduce Guardat Transactions. A Guardat transaction provides a mechanism to atomically update one policy-compliant state into the next. Transactions bundle multiple accesses to files and perform the evaluation at the commit transaction point. Reads, of course, are immediately evaluated as usual. In case of a successful policy evaluation, Guardat atomically updates the metadata to protect the newly written file. Every transaction has an in-memory cache. This cache stores relevant policy information, such as content hashes, and third-party certificates. These transactions are what make policy evaluation efficient, since all required information is actually in memory. So let me walk you through an example. Here we are using the protected executable. So let's recall, to avoid installing Trojans by attackers, we allow only signed vendor updates requiring a cryptographically signed certificate. In Guardat, an untrusted application has to show policy compliance. So for this, we use a software update application that first would try to download the new executable and the certificate from the vendor. It would then initiate a transaction with Guardat that initializes the transaction cache with the policy from the Guardat metadata, as well as the certificate from the application cache. Afterwards, the untrusted application would start writing the new executable, while Guardat computes the hash of all data that is being written, and at the end puts it into the transaction cache. The application then commits the transaction, which causes Guardat to evaluate the update permission of the existing executable. Basically comparing the hash that was computed by Guardat with the hash in the signed certificate from the vendor. In case the hashes match, Guardat atomically moves the metadata to the new executable, and from this point on, protecting the new executable. Otherwise, it would stay same. Okay, so let's take a step back and see what we have accomplished by this design. The entire overhead of demonstrating policy compliance is now shifted towards an untrusted application, thus removing complexity and computational overhead from Guardat into an untrusted application running on the host. Okay, so with this design in mind, I would like to show a little bit more details about our prototype implementation and evaluation. We implemented Guardat as a storage area network server. Other alternatives would have included disk or RAID controllers, SATA or SCSI adapters, or an implementation within a hypervisor. We chose the Linux iSCSI Enterprise Target Server due to its availability and the possible physical separation from a host system. We modified the iSCSI Enterprise Target Server, which is a kernel module implementing an efficient SAN server, such that we added a trusted controller within about 20,000 lines of code. Our metadata is always stored on a fast flash device. In this talk, I'm focusing only on the overhead compared to a plain iSCSI implementation providing no protection at all. We challenged Guardat through several synthetic and real-world examples. For the synthetic workloads, we protected 3.8 million files on the disk and associated one of the 40,000 policies with them. The first experiment that I would like to show is an SSD throughput experiment, where we see that the overhead is at most 2% for read and write accesses. Next, we measured the guarded latency. To do this, we made very small 512-byte accesses in multiple configurations. When the data is stored on a hard disk, the overheads are all less than 1%. When the data is stored on a solid-state drive, though, the result depends on the access patterns. For sequential accesses, Guardat's in-memory caches are very efficient, and thus the overheads are again negligible. For random accesses, though, the caches are less effective, and we see up to 100% overhead. Let me note, though, that this is a very extreme workload with tiny accesses, and once we increase the access size, the overheads diminish quickly. To show a real-world application, we built protection around an Apache web server. It's protected similarly to the threats shown during the introductions. Log files are append-only, executables may only be updated through a signed vendor update, and content pages are allowed only to be updated by their owner. This required about 50 lines of code to be added to the Apache web server. As content, the web server hosts the entire English Wikipedia corpus, about 220 gigabytes of data, including 15 million files. We generate access patterns for these documents based on an hourly access distribution from Wikipedia. Under this environment, at about 60 concurrent clients, which is the peak throughput for iSCSI, we see an overhead of about 2%. This shows that Guardat can be used with today's applications, and it is efficient in web server scenarios. Okay, so in conclusion, Guardat provides the means to protect confidentiality and integrity for the persistent data and state. It is independent of higher software layers such as the application, operating system, and network, and allows to physically protect the entire compliance system. While I mainly focused on the example web server, it is general to any computer system and protects unauthorized accesses, installing Trojans, and log manipulations. Despite its strong guarantees, we have shown a SAN server implementation which is efficient. So with that, I would like to thank you for your attention and be happy to take questions. Also, me and my co-authors will be happy to answer your questions later on.
Peter Beetz of Imperial College London. So yeah, thanks for the talk. I have two questions. So my first question is, do you assume that the authentication logic can be trusted? Because when you enforce a policy, you get information about the session.
So, I mean, the session establishment is based on a public-private key pair in this case, and the crypto behind it, of course, has to be trusted.
Okay, so you essentially assume that a malicious attacker wouldn't essentially, be able to spoof the identity and pretend to be another user.
Yes, the key integrity has to be maintained. Correct. Okay.
Oh, I see. So there's essentially a separate authentication mechanism against the controller. Okay. And my second question is, so when you look at an entire application stack, you will have authorization policies at different levels, right? I mean, there's the file system that will do access control checks. There'll be the web application. How do you ensure that all of those policies stay well, consistent with the policy that you have at the storage layer?
So the guarantees that we provide at the storage layer, especially for authentication, are the ones that are concerned with the end user, right? So if you store a private file, it is important that the end user who wants to access that file or the set of end users have access to that file.
Okay, thanks.
Winfried Kühnhauser, Technical University of Ilmenau. I actually have two questions also. First question is about your policy language. Okay. The policy, you gave some snapshots of that language. Is it powerful enough to express any attribute-based access control policy?
Okay.
It seems you are using attributes of people, of files, things like that, in order to make your access decision, right?
Yes. So, I mean, the policy itself has about 40 predicates that allow access to various things. As seen, they allow access to who currently is authenticated to the system, sure. Information about the file, the transaction that is going on, content that is stored on the system, and of course also that's, in addition, third-party certificates, right? So depending on how you specify your attributes, yes, we could, I mean, if your attribute space is included in that, then yes.
Okay, next question is follow-up. Once you have a formalized access control policy, could we start now, based on that policy, in trying to prove properties of the policy? Like a property given a certain protection state. Is it ever possible that starting from this protection state, some user Alice may gain the right to access some file?
We have not formally proven our policies yet, but it's definitely imaginable that you could, for certain policies, do that. Especially if you look at the confidentiality policies that I showed that are based on the session is predicate. It's relatively simple even to read this policy and say session is Alice is allowed to access this file, right?
And in the future? Well, I'm interested potentially, if I have written a policy, I'm interested about, well, general properties that also are true in the future. Tomorrow, next day.
So the trusted controller ensures these guarantees in future, right? Yeah. I probably missed your point, though.
Well, the point is that some policies include behavior logics.
Yes. Like the append-only logic, right? Can I formally prove that it will never modify
things like that?
Existing
yes.
contents?
This
right?
was my idea. Yes.
We have not proven such guarantees yet.
Okay.
It would be interesting to see
yes,
whether you can do it.
Yeah. Thank you.
There's one question. We have some time. So.
Hi, Bill Belowski from Microsoft Research. So you say that you don't trust the file system, but you're looking at things at the block level. Do you assume that you're running a particular file system so that you can understand the mapping between blocks and files?
So we actually, to answer your question fully, we extended the block interface with commands that allow us to maintain a metadata assignment from block to policy, right? So by that, we sort of know which files are stored where, okay? We don't rely on any of the file system that runs on top to tell us, right? Because this is how our API basically allows us to know where these associations are made.
Okay, so you have to change the file system to add more metadata to the requests to do that.
Yes.
That's fine. And the second question is, since everybody else had two, I get two also.
We have time.
The second question is, when you do reads, do you pass up encrypted data all the way to the user, or do you do? Because otherwise you can't cache.
If it is a confidential file, okay?
Yeah.
I think I know what you're trying to hint at. But if it is a confidential file, you would establish a secure session from the client itself to the device, right? Completely to the device. You can still use the intermediate layers, the caching layers, But we would have to augment them, for example, with which client is accessing or which application is accessing this piece. And then encrypted content would be given by the device to the upper layers.
Right. So the cache would cache the ciphertext. Okay, that makes sense.
Yes.
Thank you.
Oh, another question.
Ahmed Al-Eldin from Umeå University, Sweden. My question relates to how do you set the policies? I might have missed that.
Okay.
Yeah.
So policies are set by the client applications, basically, through a particular API call once you write your data.
Okay, so is it easy to change policies for files once they are set?
So we have a particular permission in place to govern when you're allowed to change a policy, right? So you're not always allowed to change a policy, and you can even set it to never, right? So in that way, you need to be clear, and once you state a policy, how it can be changed in future.
Okay. Thank you.
Welcome. Okay.
Any more questions, or somebody has 2 questions? Okay, well, let's thank the speaker again.